Hey everybody, I'm going to solve a problem here that is from my Calculus 2 class. We're doing sequences, and this is a problem that I started at the end of a class period and didn't have enough time to finish. So I promised the class I would make a video and go through it. So I decided I would just make this public because it's an interesting problem and it really touches on a number of interesting results and things, and it's even a problem that you might see in a beginning real analysis class. Um, so the problem is stated as there's a sequence that's defined recursively. So first of all, what is a recursively defined sequence? It's a sequence where each additional term in the sequence is defined in terms of the previous terms. So you tell what the next term is by looking at the previous terms. And it's usually some kind of algebraic formula. So in this case, a1 equals 1. That's saying the first term is 1. A n sub 1 is 4 minus 1 over a sub n. That's saying that we get each additional term in the sequence by inverting the previous term and then taking 4 minus that. So what we're going to start off by doing is just calculating the first 5 terms of the sequence, just to get a feel for what's going on. Then we're going to show that the sequence converges, and we're going to find its limit. Now, those are actually two separate things, because in order to justify the calculations we're going to do to find the limit, we first have to know that it converges. So if you try and do a lot of calculations with sequences, assuming they have a limit when they actually diverge, you can end up with some stuff that's not so nice. So first we have to show it converges, and then we're going to worry about the limit. But first, let's just write out the first few terms here. So we know a sub 1 is equal to 1. A sub 2. Okay, so if I plug in n equals 1 into this recursive formula, I get a sub 2 is 4 minus 1 over 1. Because 1 was the previous term. So 4 minus 1. So the second term is 3. What about the third term? So the third term will be 4 minus 1 over the previous term. Previous term was 3. 4 minus a third, which is 11 thirds, which is 3 and 2/3. So that's going to be 3. I'll use a repeating decimal here. It's 3.6 repeating. A sub 4. 4 minus 1 over 11 thirds. So 4 minus 3/11ths. And if you get a common denominator here, it's 44 minus 3, which is going to be 41. So 41 over 11. And so what does this turn out to be? This is 3.72727272. So it's 3.72 repeating. And then finally, the fifth term then is going to be 4 minus the reciprocal of this. So I'll go ahead and just reciprocate this now. So it's going to be 4 minus 11 over 41. 41 times 4 is 164. So 153 over 41. And thankfully, this is the last term that we're asked to find. So this turns out to be, I'll just give you an approximation here. It's approximately 3.7317. Okay, so let's take a look at these first 5 terms. See if we notice anything. So 1, 3, 3.6 something, 3.72, 3.73. So it seems that the terms are increasing. And that's actually something that we're going to have to show. That is true. So these terms are increasing, but they're not increasing bigger and bigger and bigger. They seem to be settling in on a limit value, which is what we're going to find. So how would we show that this sequence actually converges? So what we have to do is actually use a theorem, and this is the result that we go over in calculus, which is something called the monotone convergence theorem. So the name of it's not really important. It's what it says that's important. So let's go over what that says. And I guess it's actually called the monotonic sequence theorem. That's what our book is calling it. So that's what we'll be calling it. So what this says is every monotonic bounded sequence converges. So there's a little bit to unpack here. We have to go over what is monotonic and what is bounded. So a monotonic sequence is a sequence that's increasing or decreasing. In other words, the terms are either getting bigger and bigger or getting smaller and smaller past a certain point. Now, the definition of increasing and decreasing, it's a slightly different depending upon who you ask or what textbook you're reading. It might allow for equality. So like in an analysis book, it might say that it's a monotonic sequence if it's constant. It doesn't have to be strictly increasing. In calculus textbooks, for some reason, they have it strictly increasing, but it's not really needed here. So every monotonic bounded sequence. So what is bounded? Bounded means that I can trap the magnitude of the terms within a certain bound. So the terms never get bigger than this amount or less than this. So maybe they never get bigger than 10 or never get less than -5 or something. So they don't have some terms that are getting arbitrarily big or arbitrarily small. And if you have these two things, then the sequence converges. Now you need both of these things. Just to give you an example, counterexample, if you look at the sequence n, 1, 2, 3, 4, 5. Okay, so just the sequence of positive integers. This is monotonic. These are increasing. 1, 2, 3, 4, 5 is getting bigger and bigger, but not bounded. And this is not a convergent sequence. So it diverges to infinity. And another example we could use would be -1 to the n. So this is the sequence -1, 1, -1, 1, and so on. So it's constantly oscillating back and forth, alternating back and forth between those two. Now this is a bounded sequence, right? The terms don't get big. In fact, they're always magnitude 1, but it's not monotonic because they're going back and forth. So there's never a point past which they're always increasing or always decreasing. And this does not converge either. This diverges. So here you can see that either one of these alone is not going to guarantee convergence. You need both of them. So this is always something you should do when you have a theorem. This is just a general thing. When you have a theorem that has a list of hypotheses and then the conclusion, check to make sure if you take out any one of those hypotheses, you should be able to find a counterexample. The only exception to that is if they're really, kind of getting a weaker result, so they pile on more hypotheses than you need to make it easier to prove or easier to state. But for most results, if you take out one of the pieces, one of the hypotheses, it should be necessary. So you should be able to find a counterexample, and here's 2 counterexamples. Okay, the proof of this is beyond a calculus class because it depends on the structure of the real number system. But intuitively, just think about if you have a bound on a sequence and the numbers are getting bigger and bigger, then they're going to start to settle in on a value, or if they're getting smaller and smaller, because they can't go to infinity, they can't go to minus infinity. So they're just going to start to settle in on something. That's intuitively what it's saying. Okay, so we have to show that our sequence is increasing and bounded. So how are we going to show that it's increasing? So this gets to another interesting part of this problem, that we have to use something called induction. So let me briefly go over a review of induction if you haven't seen induction before. So mathematical induction is a proof technique that's used to prove statements about positive integers. So if P of n, if this is a statement that's a statement about the positive integer n, then if we want to prove that this statement is true for every positive integer n, then the way we do this is as follows. So first, you have to prove what's called the base case. So we're going to prove, say, P of 1 is true. Now, you could actually start the base case could start anywhere, but for us, it's going to start at 1. So this is called the induction base. This is usually pretty straightforward. You just kind of plug in and you just verify. There's nothing really to show. The interesting step is the next part, which is the induction step. So in this case, what you do is you prove that if the statement is true for an integer k, then this means that it must also be true for the next integer k plus 1. So the analogy used is dominoes. If you have a list of dominoes that are going on forever, if you know that you hit the first domino, if you know I'm going to hit the first domino, and if you know that every domino is going to hit the next domino in the list, then what can you conclude? You know that the entire row of dominoes is going to fall. So that's the intuition behind induction. People get really confused on this step number 2 here. This is important, because in the induction step part, you assume that it's true for some value, say k, and people think this is wrong, because how can you assume that it's true for k? That's what you're trying to show. So they think that it's bad reasoning because you're assuming that it's true when we don't know that it's true yet. The point is that we're not proving that it's true for k. What we're doing is we're proving this entire implication statement. And when you're proving an implication statement, you have to assume the first part. You have to assume what comes before the implication. So it's not assuming it's true. It's saying, suppose it's true, then we're going to prove something else. Okay. So what is our P sub n here? So we're going to do increasing. So we're going to show that our sequence was increasing. So what does that mean? Algebraically, it means that a sub n plus 1, I'll say strictly bigger than a sub n, for all n bigger than or equal to 1. So this means the terms are getting bigger and bigger. So let's look at doing our induction here. So the first thing we need to do is show that the statement is true for n equals 1. So let's look. Is A2 bigger than A1? Well, we know A2 was equal to 4 minus 1. That was 3. And A1 was equal to 1. So yes, 3 is bigger than 1. This is what I was saying about how the base case is usually very easy to show. But now we need to do the second part, the induction step. So how does this work? So what we're going to do is let's assume that a sub k plus 1 is bigger than a sub k for some k. So the reason I'm not using n here is n was kind of like the dummy variable for what the statement we're trying to prove is, which is this. So I don't want to use n. I'm going to use k and then show it's true for k plus 1. Okay, let's just remind ourselves what we need to show. So NTS is my abbreviation for need to show. we need to show that this is true for k plus 1, which would mean a sub k plus 1 plus 1. So a sub k plus 2 is bigger than a sub k plus 1. So this seems a little tricky here, but what this is saying is if one term is bigger than its previous term, then we need to show that the term after that is previous than itself. So what we have to do is we have to play around with the inequalities. What does this inequality say? Well, since a sub k plus 1 is equal to 4 minus 1 over a sub k, if this is bigger than a sub k, then what this means is, if I multiply this through by a sub k, I get 4a sub k minus 1 is bigger than a sub k squared. Now, actually, now that I think about it, since I'm multiplying through by a sub k, what I'm going to actually prove here is that also a sub n plus 1 is bigger than a sub n is bigger than 0. Okay, so I'll make that part of the part of what we're proving here. Now, 3 is bigger than 1 is bigger than 0. The only reason I'm including this is here, when I multiply through by a sub k, I really should, make sure that it doesn't change the direction of the inequality. Okay, so this is what I have. Now, on the side here, this is all going to be completely on the side. This is scratch work. What do we need to show? It's the a sub k plus 2. Well, a sub k plus 2 is 4 minus 1 over a sub k plus 1. But a sub k plus 1 is 4 minus 1 over a sub k. So let's algebraically simplify this. This is a complex fraction. So it's 4 minus 1 over, so let me multiply this whole complex fraction by a sub k. So a sub k over 4a sub k minus 1. And then if I get a common denominator of 4a sub k minus 1, let's see here. Then I see that a sub k plus 2 is actually equal to 16a sub k minus 1. So 15a sub k minus 4 over 4a sub k minus 1. And what am I trying to do with this? I'm trying to show that this is bigger than a sub k, which, a sub k plus 1, which we saw was 4 minus 1 over a sub k, which really is 4 a sub k minus 1 over a sub k. Okay, so this inequality here, that's what we're trying to show. So let's see what we would get if we multiply this through by both denominators. Move this a little bit more. So we get 15a sub k minus 4 times a sub k. We need to show that that's bigger than 4a sub k minus 1 all squared. But this on the right-hand side, notice that that is 16, that is 16a sub k squared minus 8a sub k plus 1. And if we kind of collect all the terms together to see what we got, if we subtract the 15 here, that's just going to make 1a sub k squared. And if we add 8a sub k and subtract 1, oh boy, so we end up with 4a sub k minus 1 bigger than a sub k all squared. And notice that's exactly what we have up here, right here. We know this is true. We assumed that a sub k plus 1 was bigger than a sub k, so we got this inequality right here. Notice that's exactly what I got at the bottom here. They're exactly the same. So what I have to do is kind of work my way back. Actually, I could just do a string of equivalent symbols here, but I'll write it up nicely now over here. So this, just kind of backtrack. This implies that 15a sub k squared minus 4 a sub k is bigger than 16 a sub k squared minus 8 a sub k plus 1. So this comes from this here. Well, you can just see that this is equivalent. And then I'm just going to backtrack. So this is 4 a sub k minus 1 all squared 15 a sub k minus 4 a sub k. Now I get back to this big inequality here. So now, if you were doing this on a homework assignment, just if anybody's taking a class, I'm not going to ask this on a calculus exam, but if you're taking a real analysis class and you're asked to do this, you would do this on scratch paper, and then what I'm writing up here on the left is what you would turn in, or if you're doing it on homework. You don't want this kind of scratch stuff. I'm trying to figure stuff out on the side. That's not where you're really going to turn in. Okay, and then let's see, we go back once more to, so this is 4 minus a sub k minus 1. And let's see, 4 minus 1 over a sub k. And then, and this implies 4 minus 1 over 4 a sub k minus 1 over a sub k. 4 minus 1 over a sub k. But this right here is 4 minus 1 over a sub k, so that is four minus 1 over a sub k plus 1, bigger than 4 minus 1 over a sub k. All this on the left here, by the recursive definition, this is a sub k plus 2, and all this, by the recursive definition, is a sub k plus 1. So, to back up, we started off, we assumed the k plus first term was bigger than the kth term. We expanded out what that inequality was saying. And then we got, after playing with the inequalities a whole bunch of times, kind of knowing in advance what direction we were going in, we got that the k plus second term is bigger than the k plus first term. So that completes the induction. And so by induction, we've shown that it's increasing. Now remember, that's only half of what we have to show. We also have to show it's bounded. The bounded part is not nearly as bad. The increasing part is really where you have to play around with the inequalities the most. So let's now show that it's bounded. All right, now we need to show a sub n is bounded. So if we're going to show it's bounded, we need a bound. So actually we're going to show it's bounded above. because we know all the terms are positive. So actually, we know it's bounded below by 0. So actually, we're going to show that a sub n is less than or equal to 4 for all n. Okay. Now, why choose 4? Well, we saw that the terms were starting to settle in on 3.7 to 3.73 something, somewhere around there. So it seems like 4 should be an upper bound. Okay, so again, remember our induction. Is A1 less than or equal to 4? Yeah, A1 is equal to 1. So definitely the first term is less than 4. In fact, you can even see that the first few terms are less than 4. So certainly we got the base case here. Now we're going to suppose that a sub k is less than or equal to 4. Okay, now again, on the side, let's see, what do we need to show? We need to show the k plus first term is less than or equal to 4. Remember that k plus first term is 4 minus 1 over a sub k. We need to show that's less than or equal to 4. This part is not nearly going to be as bad as the increasing because we're just going to play around with the inequalities. If you look at this, I can kind of see exactly where I need to go. I need to invert. So these are both positive numbers. When I invert positive numbers, the inequality switches. Right? Think 2 is less than 3, but a half is bigger than or equal to a third. So 1 over a sub k is bigger than or equal to 1/4. Okay. But then I have the minus sign here. Now, if you have an inequality, you hit it with a minus sign, it changes the direction back. So it's going to change right back. Minus 1 over a sub k is less than or equal to minus 1/4. Okay. And then I'm taking 4 minus that. So I'm just going to add 4 to both sides. So it's saying 4 minus 1 over a sub k has to be less than or equal to 4 minus 1/4, which is actually 3 3/4, so that's 15/4, which is strictly less than 4. Okay, so now we've got this is a sub k plus 1. So we started off with a sub k less than or equal to 4. Then we got a sub k plus 1 is less than or equal to 3 3/4, which is less than 4. So it's less than or equal to 4. So if the kth term is less than or equal to 4, the next term is less than or equal to 4. That's the induction step for being bounded. So by induction, our sequence is bounded as well. Okay, so now we get to use the monotonic sequence theorem, which we talked about, because we have a monotonic with increasing bounded sequence. So we can say by monotonic sequence theorem, we know that it's convergent. Okay, so we know it converges. What's the limit? What does it converge to? Now, this is an interesting trick, because what we're going to do is look at the recursive definition, so the one that defines the k plus 1 term in terms of the kth term, and we're going to take the limit of both sides as k goes to infinity. This is the reason why you need to know it's convergent. When I take the limit, I need to know that limit exists. So I can't say this limit is equal, the limit of this is equal to the limit of this if I don't even know that the limits exist. But now that I know that the limit exists, I can do that because I know I have a limit. So now let's look at this. Actually, I'll change it to n. So a sub n plus 1 is equal to 4 minus 1 over a sub n. Take the limit of each side as n goes to infinity. Okay, so in other words, the limit as n goes to infinity of a sub n plus 1 then has to equal the limit as n goes to infinity of 4 minus 1 over a sub n. Okay, but what are these? And actually, let's call also, let's let L, so we'll actually give a variable to it. Let's let L be the limit of the sequence. Well, what's the limit of a sub n plus 1? Well, really, it's the same as the limit of a sub n. Because as n goes to infinity, n plus 1 goes to infinity. So this whole left-hand side here is just the limit of the sequence. So L is equal to, now, by the properties of limits, the limits work well with algebraic operations. So the limit of the difference is the difference of the limit. So 4 minus, and then what's the limit of 1 over a sub n? Well, as long as our limit is not converging to 0, as long as the limit's not 0, then it's going to be 1 over the limit. And we don't know that our limit's not 0 because we know that the terms are increasing and like the second term is 3. So we know that this is converging to L, which is not 0. So 1 over that is converging to 1 over L. So that means L, the limit, has to be equal to 4 minus 1 over L. This is a nice little equation now that we can solve for L. Ends up being a quadratic because we can multiply through by L. And we get L squared is equal to 4L minus 1. Okay, so L squared minus 4L plus 1 is equal to 0. Does not factor. You have to use quadratic equation. L is equal to, so quadratic formula would give us minus b plus minus square root all over 2a. So this is going to be root 12, which is going to be 2 root 3. So we got 4 plus minus 2 root 3 over 2. However, if we do 4 minus, well, let's simplify this. This is going to be 2 plus minus square root 3. If we were to take the minus, that'd be 2 minus square root 3. That'd be less than 2. We know the limit can't be less than 2, though, because the second term was 3 and it's increasing. So in fact, out of these two, the choice has to be positive. It can't be the negative. That just doesn't make sense. So we get the limit, finally, of our sequence is exactly equal to 2 plus square root 3. And 2 plus square root 3, so this is approximately equal to 3.73205. Okay. So if we compare that to our first 5 terms, see, we calculated up to the 5th term. The 5th term was 153 over 41, 3.7317. And the exact value of the limit is 2 plus square root 3, which should be a little bit bigger than that. 3.73205, which is slightly bigger than that. Okay. So that finishes the problem. We proved that it's convergent, and we calculated the limit of 2 square root 3. So I hope you enjoyed this problem. Puts together a lot of different topics, puts together induction and things about sequences, monotonic and bounded sequences, and even the quadratic formula. So hope you liked it.